Hello everyone, welcome to another video. This video is about multi-objective optimization problem. This group of optimization problem involves several objective functions which their value should be optimized. It is like parallel optimization and it means that we want to optimize the value of different objective functions at the same time. For example, when we want to minimize cost, time, and error in an arbitrary evaluation. And it is really important problem in economic, for example, and also in optimization control, optimal control area, or in lots of different area. Since this problem involves a different objective function, solving this group of problem is not too easy like a normal optimization problem. And we need to find a point which is optimal for all objective function. We have here two different approaches. The first one is Pareto method and the second one is scalarization method. A mathematical formulation for a multi-objective problem is like that we have here several objective functions which their value should be minimized or maximized at the same time. And we know that these two operations are almost the same. And we have here several conditions for our inputs and also a lower bound and upper bound for our inputs. Here we need another definition which is really important because the goodness of our solution determined by this definition, and it is dominance. We need to define here a dominance test, and it means that x1 is dominated x2 if solution x1 is not worse than x2 in all objective functions, and also x1 is strictly better than x2 in at least one objective function. And finally, x1 dominates x2 if and only if x1 is determined by x1. So we know here what means dominated point and non-dominated point. Non-dominated means that there isn't any other point in our visible area which is better than our non-dominated point. So, in order to find Pareto optimal solution, we need first of all to define a non-dominated set in feasible decision-making area, and we should find our optimal value in this non-dominated set of inputs. Here we can maybe understand these definitions better. For example, here we have Pareto optimal solutions, this point. But what means here? Here is our feasible decision area, and it is here our input area. And here we have output and two objective function f1 and f2, and we want to minimize their value at the same time. Here we have a Pareto optimal front which is according to the value from these points from our feasible decision space, and we should find our optimal value from this area. Okay, after finding this Pareto optimal front, we can find our optimal value, and the final goal is finding a set of solution as close as possible to Pareto optimal front. And the optimal value can be determined by finding the shortest Euclidean distance. And so we have here, first of all, a set of non-dominated point from our feasible decision-making space. And here we have Pareto optimal front. And by this formulation, Euclidean distance, we can find our optimal value. In the second approach, escalarization method. In this method, we defined a function like that which is a linear combination between all our objective functions. And W1 to Wn are our weights. And we can find our optimal solution by finding optimal value for these weights. The weights determine that how important an objective function is. For example, a large weight determine that the effect or priority of this objective function is high, and a smaller weights means that this objective functions um has lower importance. And we have here three different methods to find these weights, and they are these two methods: equal weights, ROC weights, and RS weights. These two methods are used to find optimal value for weights in this method. In this method, we have an advantage, and it is that method is really simple. And but we have two different and important disadvantage. Um, the first one is that we cannot use these methods for non-convex optimization space. And another is it is difficult to set the weights vectors to obtain a Pareto optimal solution in a desired region in an objective function, because in this method we made a solution, but in the first method, we search our optimal value from an existing area of solutions, of non-dominated solutions. Finally, as a conclusion, in Pareto method, we find the optimal solution from a set of existing non-dominated solution. But in a second method, scalarization method, we create a multi-objective function, and by using weights or determining weights, we find a single solution for our objective function. I hope you find this video helpful, and if you find this video useful and that was good for you, please like it and subscribe to my channel. Thank you. Bye.